in the chapter Spectroscopy C, we are going to talk about nuclear magnetic resonance, which is a very versatile way to determine the carbon-hydrogen framework of organic molecules. It also has, I think, a really neat application in medicine. It is used as an MRI. So if you've had an MRI, you have experienced nuclear magnetic resonance. And so here's an example of an MRI machine, and then the image that an MRI machine can give you. So this is a really neat medical application of NMR. So then what is NMR? Nuclear resonance spectroscopy, which is abbreviated NMR, is a really powerful analytical technique that is used to characterize organic molecules by identifying the carbon-hydrogen framework within the molecules. Two common types of NMR spectroscopy are used to characterize organic structures. One is a proton, that's a 1 right there, NMR, right? And this is used to determine the type and number of hydrogen atoms in a molecule. And then the second type is carbon-13 NMR. And this is used to determine the type of carbon atoms in a molecule. So the source of energy in NMR is radio waves. Which is a lot of times going to be abbreviated through your book as RF, radiation. Okay, and these generally, remember, have long wavelengths, and so they're really low in energy and frequency. Now, with these low energy radio waves, they interact with when they interact with a molecule, they can change the nuclear spin of some elements, including the proton and carbon-13. So when low energy radio waves interact with a molecule, they can change the nuclear spin of some elements, right? Including the proton and the carbon. Now, when a charged particle like a proton spins on its axis, it creates a magnetic field. And when it does this, it causes the nucleus to act like a tiny bar magnet. And so we represent that kind of is the magnet here, and then that's the nucleus, okay? And so all of these little guys that are shown here are going to be those protons. Now, normally these guys are just randomly oriented in space, right? They're just pointing every which way of direction. However, when you put them in a magnetic field, and a magnetic field is abbreviated B naught, okay, they will orient either with the magnetic field this way or against the magnetic field this way. Now, most nuclei are going to orient with the magnetic field because that's lower in energy. Kind of like view it like swimming downstream. It's a lot easier to swim downstream than it is to swim upstream. So if they're aligned against the magnetic field, those are going to be higher in energy. Now, the energy difference between these two states is really very small, right? But, right, now we have two energy states. So let's give some words to that. A lower energy state with the nucleus is aligned in the same direction. And then you could have a higher energy state left out same direction as the magnetic field is B naught. You could have a higher energy state where the nucleus is aligned against that magnetic field, or B naught, right? So it's like swimming against the current. So when an external energy source, right, kind of shown here as H nu, that matches the difference in energy between the low and the high state is applied, that energy is absorbed. And when that energy is absorbed, it causes the nucleus to spin flip. And it goes from being aligned with the magnetic field to now being in the higher energy state, and it's aligned against the magnetic field, okay? The difference between these two nuclear spins corresponds to that low radio frequency region of the electromagnetic spectrum, okay? Now, we say that a nucleus is in resonance when it absorbs radio frequency radiation and spin flips to a higher energy state. There are two variables that characterize NMR. Okay. One is the applied magnetic field. Which is, of course, B naught. Now that strength is measured in Tesla. And then the second is the frequency of radiation. That's used for the resonance. Now, this is going to be measured in hertz, or you're going to see now sometimes megahertz. Okay. So, let's talk about that resonance frequency for just a minute, or the frequency of radiation. The frequency that's needed for resonance and the applied magnetic field strength are proportionally related. Okay. So here are two variables and they're related proportionally. So what does this mean? This means that the stronger the magnetic field, the larger the energy difference between the two nuclear spin states, right? And therefore, you need a higher frequency for resonance. Okay, so NMR spectras are a lot of times referred to by their resonance. So like 300 megahertz instruments or 500 megahertz instruments. And so it really depends on the frequency of the RF radiation used for resonance. These spectrometers use really powerful magnets to create a small but measurable energy difference between those two possible spin states. So this is a schematic of an NMR, right? And so a sample tube is loaded into the NMR here. Now the sample is dissolved in a solvent, right? And the NMR tube is really, really thin. The magnet is here. And the sample is going to be rotated in a magnetic field and then irradiated with short pulses of that RF radiation. And then you get an NMR spectra from this. Now, if all protons absorbed at the same frequency in the magnetic field, the spectra of all the compounds would just consist of a single absorption. And that would make the NMR useless, right? Because one peak doesn't help us. However, that's not the case. All protons do not absorb at the same frequency. They're slightly different. And so that is really helpful for us. So the frequency at which a proton absorbs is determined by its electronic environment. And so what do we mean by this? Well, because electrons are moving charged particles, they create a magnetic field opposed to the applied field. So that means that protons in different environments absorb slightly different frequencies. And because they absorb slightly different frequencies, we can see them in the NMR. Now, the size of the magnetic field generated by the electrons around the proton determines where it absorbs. right? Modern NMR spectrometers use a constant magnetic field strength, and then a narrow range of frequencies are applied to achieve the resonance of all the protons, and so that's what separates the peak out. Now, only nuclei that contain odd mass numbers or odd atomic numbers will give NMR signals. So let's look at an example of an NMR spectra. So this is an example of an NMR spectra. It's a plot of intensity shown here on the y-axis against the chemical shift, which is shown here on the x-axis. When we talk about the chemical shift, that is measured in parts per million, okay? So that's going to be the unit for the chemical shift. We start over here, right? And so we have the right side here, and we generally read from the right to the left. We refer to the right side as the up field this way, and then the left side as down field, okay? So if you think about it, you're going to travel this way and you're going to travel downfield. Okay, so upfield and downfield. The lines here that are shown are the peaks. I want to point out that you have a reference sample here. So the reference sample, right, is an external sample that's added to the tube prior to the NMR. So it's called TMS, right? And that stands for tetra methyl silane. And that's, again, just added to the tube prior to the NMR measurement. And the NMR absorptions are measured relative to the position of that at 0 parts per million, right? And so what we're going to see here is this is just an involatile, it's a volatile inert compound, and it just gives us a single peak. Now, most protons are going to absorb between this 0 and 10. And again, we're talking protons, we're not into carbon yet. So let's put some words to that, right? Most protons absorb between 0 to 10 parts per million, right? We use the term upfield, which means to the right, which is a higher magnetic field. And downfield, which is to the left, and a lower magnetic field. Right, to describe the locations of the peaks. And then I've already mentioned and talked about that external standard, which is TMS, which helps us see where the peaks are on the spectra, and it helps us have a uniform NMR from instrument to instrument. Now, I want to talk about the chemical shift just a second. So the chemical shift gives us that position of the NMR signal. And I've already mentioned it's measured in parts per million. And this is how you can calculate it. So you take the observed chemical shift in hertz, right, downfield from tetramethylsilane over the frequency of the NMR spectra. So, for example, let's say, right, we need to calculate the chemical shift of the absorption that occurs at 1500 hertz downfield from TMS using a 300 megahertz NMR spectrometer. So to calculate this, we would come here and we would say, great, we're going to take 1500 hertz. That's the observed chemical shift downfield from TMS. Divide it by the frequency of the spectrophotometer, which is 300, right, megahertz, and that gives us 5 ppm. Okay. Now, we report that NMR absorption as a fraction of the NMR operating frequency, and that's what gives us the units ppm, and that makes this independent of the spectrometer.